doesn't matter. Okay, thanks everybody. I would like to thanks for sure the invitation and the organizer. I really proud to be here to participate in this first mNIRS meeting, and I was also happy to see this facility because I've never been in Essex and in Colchester, and I think this university is really cool. So first of all, I need to do some disclosure. So I do love NIRS because is the first equipment that I had the lucky to be involved as a MD student with the group of Bruno Grassi. So all the things that I will say are coming from someone that really trusts on NIRS. The second thing is that I'm muscle physiologist, so I'm coming from exercise physiology and medicine, so I don't have a deep knowledge on the physics behind. I'm still working with someone that has more experience on that, but I still have to learn a lot. And all the data that I'm going to present are coming from CW NIRS. And I think that this is something that we need to keep in mind because probably we are not getting the real details of all the measurements that we have. So my first part of the title is related to oxygen cascade. So I think that it's important to remember that when we are talking about signals that is coming from the muscle, we are just getting the last step of the oxygen cascade that is starting from the ambient air where oxygen is taken up by the lungs, and then this oxygen has to be transported by the cardiovascular system up to the skeletal muscles. So when we use NIRS, we are trying to get insights that happens at the level of the muscle, but we have to keep in mind always that is only a consequence of something that is happening before. And if all the processes that are happening before do not have any impairments, probably what we are seeing is a consequence of an impairment at skeletal muscle level. And when we focus at skeletal muscle level, we usually, or in the past, we were focusing more on the mitochondrial function and the muscle bioenergetics, but we have to keep in mind also that what happens in the muscle has to match with oxygen delivery. So it's always a match between what is bring to the muscle and what is taken up, and it goes through a process that is muscle diffusion, which is something that in the last part of my presentation we try to address. The second thing I think that is important to remember is that when we are talking about running, cycling, and whole body exercise, the main limitation usually rely on central components. It has been estimated that the role of limitation at central level are around 70%. So the muscles are playing a role, but they are playing a very limited role. The situation changes a lot when we are talking about small muscle mass exercise, and we just heard about the resistance training, so that's something that can be explored, or when there is a disease that maybe can highlights or increase the importance of the skeletal muscle mass. So if we look on the oxygen cascade and we try to combine all these elements as a machine, what has been highlighted by physiology is that what is happening at the level of the muscle is a consequence of several gears working one together with the other, where oxygen is taken up by the lungs, is transported by the cardiovascular system up to the muscle, and then is taken up by the mitochondria to be utilized and produce ATP. From a mathematical point of view, this is classically expressed by this principle where oxygen consumption is equal to the cardiac output times the difference in oxygen between arteries and veins. But if we look on the peripheral side of this design, we know that the amount of oxygen that is consumed by the muscle depends from the difference between the partial pressure of oxygen between the arteries or the capillaries and the internal ambient of the skeletal muscle cells. So from a mathematical point of view, we also say that the muscle oxygen consumption is related to the product between the ability of oxygen to move across the membrane and reach the mitochondria, and the difference in pressure between the capillaries and the mitochondria. If we assume that the mitochondria, the partial pressure of oxygen in the mitochondria is equal to 0, and we have some evidences to be sure that it's very close to that, we can express this relationship without taking into account the pressure inside the mitochondria. These two equations, if you compare, they are all giving you oxygen consumption. So it means that they can be combined. And this has been done by Professor Wagner in a unique diagram where you have the perfusive, so the amount of oxygen that is delivered to the muscle that is represented by a sigmoidal curve, because the amount of oxygen that is taken up, it depends from the ability of the hemoglobin to transport oxygen to the muscle. And this represented, oh, you cannot show my arrow. Okay. Yeah, it's better. And is classically represented by this line. And the ability of the muscle to take up oxygen from the capillaries is usually represented by this line, where so the point where these two lines convene is represented by the oxygen consumption. And we know that whenever we modify the situation, for example, we do exercise training, we have an increase of oxygen or maximal oxygen consumption that is due to an increase of cardiovascular factors, usually cardiac output, and also sometimes an increase of the ability of oxygen to diffuse at the level of the muscle, which classically is associated to an increase of capillarization of the muscle. On the other side, when we consider patients, we can observe a reduction of maximal oxygen consumption that can be due to a reduction of the cardiovascular system ability to transport oxygen, but also to a reduction of the ability of oxygen to diffuse at the level of the muscle, like muscle atrophy or rarefaction of capillarities. So how we can know the role of the peripheral factors? In the past, there have been used many different methods, and usually these methods were invasive. For example, we can take muscle samples and we can study the histology and look at the number of capillaries for single muscle fibers. We can look at the type of muscle fibers, or we can also permeabilize muscle fibers and make the mitochondria able to consume oxygen and measure the oxygen consumption of the mitochondria. If we want to do this during exercise, this complicated a little bit the situation, but in Scandinavia, this has been done. And for example, you can put some catheters in the artery and the veins and make the subject exercise and measuring not only the oxygen consumption at the mouth, but also the change in oxygen content in the arteries and the veins coming up or drawing blood from the lower limbs. But this, you know, is really complicated. So can we use something else? Yes, I think we can have a way to estimate these factors, and I think that NIRS can help us. How NIRS can give us information? I think that these are three important elements. First of all, we can estimate the ability of muscle to extract oxygen, and we show you some of the data that we have collected. We have already heard since yesterday the ability of NIRS to be used as methods to evaluate, estimate mitochondrial function or muscle oxidative capacity. Sorry, Bruno Grassi, I'm talking about capacity, but I hope that nobody will tell him about that. And we can also probably play a little bit with the measurements of muscle oxidative capacity and have an estimation of diffusion limitation of oxygen flux at the level of skeletal muscle level. Let's start from fractional oxygen extraction. What we usually have done is to put near-infrared spectroscopy on a muscle that is used during exercise, classically vastus lateralis, and measure the changes of the oxyhemoglobin during exercise. This is a classically pattern that you can observe during an incremental test where you have a constant work rate phase and then an incremental phase. What we usually do is to calibrate the equipment with a physiological calibration. So we usually do a prolonged ischemia at the end, and we compare the amount of the oxyhemoglobin obtained during ischemia compared to what is obtained during exercise. And so a normal subject is very, very close to the maximal amount that we can measure. A subject that can have an impairment of ability of oxygen of the ability of the muscle to extract oxygen has usually a lower percentage. We have applied this in different situations. For example, a very insightful application is the situation where patients have a disease localized at the level of the muscle. So we have a myocardial disease where there is an impairment of taking up glucose from glycogen inside the muscle cells, or mitochondrial myopathies where the respiratory chain is impaired and so mitochondria cannot use oxygen. These patients usually refer exercise intolerance, which is a very general symptoms, but they need to be that you need to reach a diagnosis, and usually they have to face a muscle biopsy. So in these works, we asked to ourselves, can we, I don't know, predict with a larger ability compared to the symptoms, which is very broad, the presence or not of this disease? We applied, we recruited this subject, they came to the lab, we asked them to perform a maximal exercise test, and we applied near-infrared spectroscopy on their skeletal muscle, and these are the data. So these are control subjects of the same age. These are patients with mitochondrial myopathies of myocardial disease, and you see that the amount of the oxyhemoglobin as a percentage of the physiological calibration is definitely lower compared to the control subject, and is also lower compared to subjects that do not have the disease, but they refer exercise intolerance. And when you compare oxygen consumption with the data obtained at NIRS, you see that there is a quite good correlation suggesting that the impairment in the exercise capacity is related to an impairment in the skeletal muscle. We applied also this technique to subjects that were forced to stay in the bed for 35 days. We really like to perform these studies that are usually used by European or Italian space agency, and we measure exercise capacity immediately before and after this bed rest. As you see, the maximal oxygen consumption was reduced, and if we look to the behavior of the change of the oxyhemoglobin and myoglobin during exercise, we see that after bed rest, we have a reduction of the maximal amount of oxygen that can be extracted by the muscle, which means that the muscles are impaired. For sure, in this condition, you have an impairment also of the central component, but we can also highlight this impairment. So I think that the first take-home message is this one. So we can use NIRS to have an estimation of peak fractional oxygen extraction, and so quantify an impairment that is occurring at skeletal muscle level, both in patients or in healthy subjects that have an effect of different interventions. Then we can also have, more recently, it has been developed a system to estimate mitochondrial function by near-infrared spectroscopy. As Professor McCulley said yesterday, this comes from very early studies where the NIRS was applied on the forearm, and the NIRS signal was collected during repeated transient ischemia immediately after exercise. I thought that it could be something useful for you to see how the test is performed. This is a very rough example, but just to give an idea. So we usually ask the subject to perform an exercise. The near-infrared is on the gastrocnemius, and here you have the pressure cuff that can be pumped up with different times, and unluckily it's not really easy to see, but you can measure the changes in the TSI signal during the cuff occlusion, and by that calculate the muscle oxygen consumption during time, so in the recovery from exercise. And as already highlighted, it has been demonstrated that this is a very reliable approach. You have 2 trials of the same measurements in the same subjects, and you see that the data are really reliable, and is also a valid approach, because if you compare the constant of recovery that can be collected by this approach to the oxygen consumption that you can collect in the respirometry, so taking up muscles and measuring mitochondria, you can observe a pretty good correlation with these 2 measurements, and this has been confirmed also by our data. As already summarized, this approach has been applied in different conditions, in different muscles, and is a really valid approach. We also contributed to the field. We then tested the subject, now not after 35 days, but after 10 days of bed rest. So we placed them, young, healthy subject, on the bed. We measured before and after the oxygen consumption of the vastus lateralis with this approach. So physiological calibration and then repeated transient occlusions of the artery. And we also took muscle biopsy on these subjects to compare the results. And what we observed is that after only 10 days, we didn't observe any changes in the recovery constant, which is an estimator of the mitochondrial function. And this was confirmed by measurements of the mitochondria taken up by muscle samples. So there is, again, a good correlation, but for sure, if you are a subject, you prefer to do this one instead of doing a muscle biopsy. Marianna has presented some data during the flash talks, and I hope you had the time to go to talk with her. We have also collected this data in different populations. So this is the setting that we have established. This is a classical trace, and we collect the different slopes in a specific range. This is the point represents each slope, and you see that patients with different neurological diseases have an impaired mitochondrial function compared to subjects that are healthy of the same age. So I think that is quite easy to say that even if the subject cannot perform a maximal exercise, and so we cannot test the peak fractional oxygen extraction, we can have information about what happens at the level of the muscle by NIRS, by this approach of measuring muscle oxidative capacity. But as I said before, one of the main determinants, or one determinants that we are forgetting, is muscle oxygen diffusion. So we know that oxygen has to move across the membrane. So, and we know that these elements can change. During my course, I had the pleasure to have Andrea working as a PhD student in my lab, and we asked ourselves if changes in MVO2 in a different region of TSI, so in a condition where we have a lot of oxygen or a condition where we have lower amount of oxygen, the changes in MVO2 are related to the ability of oxygen to diffuse in the skeletal muscle. So we asked the subject to exercise, and then immediately after exercise, we will perform the repeated arterial occlusion test. We performed this test in 2 parts, 2 sections, 2 ranges of the physiological calibration. One that we can assume is let the oxygen to be available for the muscle, and the other one where the amount of oxygen available should be lower. We also took muscle biopsy in these subjects, and so we compared the numbers that we obtained by NIRS together with high resolution respirometry, so ability of mitochondria to use oxygen, and indirect measures of capillarization, which are a good estimator of diffusion capacity. As you see, when you measure muscle oxygen recovery kinetics in the high condition, you have higher number than in the low condition. So there is something that is happening. And when you keep the relationship between the K value in the high range or the K value in the low range, you see that they are well correlated to the oxygen consumption of mitochondria only in the high condition. So there is something in the low condition that is happening. And if you keep the measures, and if you keep in consideration the amount of capillaries, you see that the subjects that have lower capillaries, so lower diffusion capacity, have lower the difference in K, so they change more K. Whereas in the subject that have more capillaries, the change is higher. So there is a correlation between the changes in K and the ability of oxygen to diffuse at the skeletal muscle level. Is this valid when it's applied? I think yes. We have done some studies until now. This was a study where we compare endurance and strength training athletes, assuming that for sure the strength athlete would have larger muscle fibers, lower capillaries, and so an impairment of diffusion. In these subjects, we ask and we measure maximal oxygen consumption, force, and we also did this study, this time with 3 ranges, not anymore 2. And what we observe is for sure endurance athletes have higher oxygen consumption, lower muscle force compared to resistance. But when you look at muscle diffusion capacity and K, you see that the K values, so the mitochondrial function in endurance athlete is usually higher compared than resistance athlete. But if you look on the slopes, which are a indirect measure of the changes in K in the different ranges, you see that they are reproducing almost what we can assume is occurring between resistance and endurance athletes on the Wagner diagram. So we should have, or we can have an indirect estimator of the diffusion capacity. And so the take-home message of this last part is that it can be a promising approach also to evaluate diffusion limitation to oxygen flux in the muscle. So to give to the conclusions, I think that NIRS provide us a non-invasive methods for assessing both muscle oxidative and oxygen diffusion capacity, which are the last steps of this oxygen cascade, in healthy condition and chronic disease. So clinicians and all the people that are interested in understanding more of what happens in the muscle should use this approach. I think I had to thank all the colleagues that were involved, all the students and postdocs that collected the measurements, so spend a lot of time on this, and thanks you all for the attention.
Thank you. Thank you, Simone. So there's time for 1 or 2 questions.